functions to data. Essential question. What are the ways to model data using an exponential function of the form f of x equals a times b to the x power? Well, we're about to answer that. Identifying exponential functions from tables of values. Notice for an exponential function f of x equals a times b to the x power that f of x plus 1 equals a times b to the x plus 1 power. By the product of powers property, a times b to the x plus 1 equals a times b to the x times b to the 1 power, which equals a times b to the x times b, which equals f of x times b. So f of x plus 1 equals f of x times b. This means that increasing the value of x by 1 multiplies the value of f of x by b. In other words, for successive integer values of x, each value of f of x is b times the value before it, or equivalently, the ratio between the successive values of f of x is b. This gives you a test to apply to a given set of data to see whether it represents exponential growth or decay. Each table gives function values for successive integer values of x. Find the ratio of successive values of f of x to determine whether each set of data can be modeled by an exponential function. All right, so what we're going to do, let's see. Let's look over here. It says f of 1 divided by f of x. So that's going to be 4 over 1, which is 4. So we'll put a 4 here. All right. And then f of 2 is 16 divided by f of 1, which is 4. That is 4. F of 3, that's going to be 64 over 16, which again is 4. And 256 divided by 64 is 4. All right, good. The data are exponential. The data are exponential. Let's take a look at B. Let's see here. 7 divided by 1 is 7. And then 13 divided by 7, 13 divided by 7. Well, that's just 13 over 7. And then 19 over 13, that's just going to be 19 over 13. And 25 over 19 is just 25 over 19. That's not exponential, or not exponential. C. Take a look at this in here. So the first one, that's going to be 4 over 1. That's just going to be 4. All right. And then 13 over 4. 13 over 4. That's just going to be, well, that's just 13 over 4. Right? And then the next one, that's 28 over 13. And then 49 over 28. 49 over 28. 7 goes in, let's see, 49 over 28. 7 goes in that 7. 7 goes in that 4. So that's going to be 7 fourths. These are not exponential. All right. Let's try D. Okay. So 0.25 over 1. 0.25. 0.25 over 1, that's going to be 1/4. let's see, 0.25 over 1 that's going to be 1/4. 1/4. And then you got 0.0625 over 0.025. And I put these in my calculator. That's going to be 1/4 as well. 1/4. And so that's 1/4. 0.015625 over 0.0625. And again, if you put that in your calculator, you get 1/4. Same thing for the last one. All right. So, and notice all four of these are the same, so they are exponential. Okay, they are exponential. In which steps does the table show exponential growth? Well, step A and step D. Okay, which shows exponential decay? Well, A was 4, which is greater than 1, so that's exponential growth. Exponential growth. And D was 1/4, which is between 0 and 1, so that's exponential decay. What is the base of the growth or decay? Well, the B was 4 in that one, and B was 1/4 in that one. In which steps are the data modeled by exponential function? In which step are the data modeled by the exponential function? F of x equals 4 to the negative x. Well, that would be D, step D. What type of function model would be appropriate in each step not modeled by the exponential function? Well, let's go back up and let's go back and look at B. There's B, and let's see here. Let's look at B. What's the difference between these two? You got 6, you got 6, you got 6, and you got a difference. You got a common difference of 6 on B. So that's linear. That's going to be linear. Step B is linear. Common difference, D equals 6. Common difference is 6. And then what was it? C. Let's go back to C. C. All right. Well, what do we got here? We got a difference of 3, a difference of 9, a difference of 15, and a difference of, what was that, 21. And then look, that has a difference of 6. That has a difference of 6. And that has a difference of 6. Okay. So what does that tell you? It tells you it's quadratic. Step C is quadratic. And that's because the second difference is 6, okay, because the second difference is 6. 4. In the introduction to this Explorer, you saw the ratio between successive terms of f of x equals a times b to the x is b. Find and simplify an expression for f of x plus c, where c is a constant. Then explain how this gives you a more general test to determine whether a set of data can be modeled by an exponential function. Okay, so kind of what we did just a minute ago. F of x equals ab to the x, right? So f of x plus c equals a times b to the x plus c, right? Which this equals a times, ab to the x times b to the c. This means increasing the value of x by c multiplies the value of f of x by b to the c power. In other words, the ratio is constant. So if the x values in a set of data differ by any constant amount, and the ratio of function values at those x values is constant, then an exponential model is appropriate. So what I'm trying to say is, if you can multiply something by something, by the same something, then you have an exponential function. Roughly fitting an exponential function to data. As the answer to the last reflect question above indicates, if the ratios of successive values of the dependent variable in a data set for equally spaced values of the independent variable are equal, an exponential function model fits. In the real world, sets of data rarely fit a model perfectly. But if the ratios are approximately equal, an exponential function can still be a good model. Example 1, population statistics. Go ahead and read through this, and then when you get back, we'll do B together. All right. B. The table shows the decline in weekly box office revenue from its peak for one of 2013's top grossing summer movies. Create an approximate exponential model for the data set. Then graph your function with the scatter plot of the data and assess its fit. Find the value of a in f of x equals a times b to the x power. So when x equals 0, f of x equals 95.3. So a equals 95.3. Find an estimate for b. Approximate the revenue ratios from week to week and average them. So we're going to take 55.9 divided by 95.3, and that'll give us 0.59. Same thing here. We're going to take 23.7, divide it by 55.9, and that's going to give us 0.42. And we're going to keep on doing that all the way down. And let's see, we get 0.55 plus 0.69 plus 0.58 plus 0.55, all divided by, and then we counted this, and there was 9 of them, right? 9, and that's going to be approximately 0.58. And all I did was I did all this in my calculator. The last one, 0.6 divided by 1.1, it's 0.55, and so on. All right. Okay. An approximate model is f of x equals, and that would be 95.3 times, and that's my A, and my B right here, 0.58 to the x power. The graph looks like a very good fit for the data. All of the points except 1, 2 weeks, and let's see here. So we've got 95.3 times 0.58 to the x, and let's see, we've got a point here, and let's see, that's 55.9 was right there, and then 23.7, and then 3, 16.4, and then 4, 8.8, and then 5, 4.8, and then so it looks something like this right here. And it looks something like that. Let's look at our calculator. This is movies, so let's go to our calculator and my documents. I went ahead and put it in. Movies. So I went ahead and put it in just like you see in the table, and then I graphed it, and it looks like that there. And we're doing an exponential model, so menu 4, 6, 8 for exponential, and then it put it in. So how close did the calculator come to us? We had 95.3, it has 86.18, and then we had 0.58 and it has 0.575. Okay, so ours wasn't too, ours was not too, it was fairly close. But this one here actually hit the numbers a lot better than the one and I'll show you the one that, let's see, let's see here, control doc, and here's the one that we did. That would have been 95.3, open, and then 0.58 x, and then it looks like something like this right here, and then we can, and menu 4, 1, and x min, we'll put -1, and 10 and 1. Y min, we'll put -1 just so we can see the axis, and then we'll do 100 on a scale of 10, and then see, here's the one that can, and that looks pretty close to what we got here. I think it does. All right, good. Your turn, fisheries. The total catch in tons for Iceland's fisheries from 2002 to 2010 is shown in the table. Can you approximate? Create an approximate model for the data set? Then graph your function with a scatter plot and assess its fit. That's not what. All right. So, what do we need? Well, let's see here. I'm going to rename these here. I'm going to rename these. I'm going to rename them 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So my f of 0, my a equals, let's see, f of 0 equals a, which equals 2.145. All right. Now I need to approximate b. So I'm going to take, let's see, 2.002 divided by 2.145, and that's going to give me 0.93, and then I'm going to take 1.75 divided by 2.002, and that's going to give me 0.87. And then I'm going to take 1.661, divide it by 1.75, and that's going to give me 0.95. And then 1.345 over 1.661, and that's going to give me 0.81. And then let's see, 1.421 over 1.345, and that's going to give me 1.06. Let's see, 1.307 over 1.421, and that's going to give me 0.92. And then 1.164 over 1.307, and that's going to give me 0.89. And then I'm going to have 1.063 over 1.164, and that's going to give me 0.91. So what I'm going to do now is I'm going to add all of those up. Let's see what we got here. We've got 0.93 plus 0.87 plus 0.95 plus 0.81 plus 1.06, 2 plus 0.89 plus 0.91. Is that all of them? That's all of them. All right. And I'm going to divide that by, how many of those do I have? 1, 2, 3, 4, 5, 7, 8. I got 8, so I'm going to divide that by 8, and that's going to give me about 0.92. I did that in my calculator. I didn't do that in my head. So my equation, so f of x will equal a, which is 2.145. I'm going to just make 15, times my b, which is 0.92 to the x power. All right, so that's my equation. And so let's see here, what do we got? So I've got to put all of these on here. And let's see, 0 is 2.145. That's going to be about right there. And then the second one is 2.002, so that's going to be just about on the line. And then 1.75, so that's probably 1.8, so 1.75 would be almost right there. And then 1.661, that's going to be like right there. And 1.3, so that's going to be just under there. 1.421, so that's going to be just like right there. And then 1.307, that's going to be about halfway between 1.2 and 1.4. 1.164, and that's going to be like right. Let's see, that's 1.16, yes, something like that. And 1.063, so that's 0.8. That's probably 0.1, so it's going to be like right there. Okay, and then it's going to look something like it's going to go something like this right here. Okay. Let's go try that in our graphing calculator. So let's see here. And new document. Yes. And then graphs. What? So we got 2.15 open parentheses, 0.92 close parentheses, x. That's going to look something like this. And so that looks pretty similar to what we drew. Okay, menu for 1. So we went -1, and we'll say 10. 1, -1, and we'll put 2, and we'll put 0.25. So it looks something, and that kind of resembles what we did. Yeah, not too shabby. What do we got here? Fitting an exponential function to data using technology. Previously, you have used a graphing calculator to find a linear regression model of the form y equals ax plus b to model data, and have also found quadratic regression models of the form y equals a times x squared plus bx plus c. Similarly, you can use a graphing calculator to perform exponential regression to produce a model of the form f of x equals a times b to the x power. So use the data from example 1, part A in a graphing calculator to find an exponential regression model for the data and show the graph of the model with a scatter plot. So let's see here. Example 1, part A. Okay, good. Now let's get our graphing calculator. So example 1, part A. Let me see if that's all right. I got that right there. Okay, so let's get our graphing calculator. And we're going to do this. Let's clear this out. New document. No. So, well, we start here at the black screen, right? All cleared out. You want to go to spreadsheets, which is number 4, and we'll put in year. Y-E-A-R. And then, let's see. Start off with 0. You can put the 1790 and the 1800 and stuff like that, but it's going to move it way up, and it's going to be just different. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that's enough. And let's go over here to B, and we're going to put POP, P-O-P for population. P-O-P. All right. And then let's put those in. What do we got? 3.9. You can round it or you can put the whole thing. I'm going to just put it into two places, 3.93. 5.31. 5.31. 7.24. 7.24. And 9.64. 9.64. 12.86. 12.86. 17.01. And I said 0.1, I'm at 7.06. 23.19. 23.19. And 31.44. And 38.56. 50.19. And then 62.98. 62.98. And then I'm going to want to go over here and put a 10 in there. All right. So now I've got the data in. Put the data in. Make sure you're inside the data here. Press on. Go to the bar graph there, and it'll give you a scatter. Come down here to the bottom and press year. Over here on the side, press population. And there you go. You have now made a scatter plot. You've now made a scatter plot, which is good. What we're going to need, though, is we are going to need an equation here. We're going to need a line and equation. The calculator will do that for you too. Menu 4, 6, and it's got a big curve to it, so we think it's exponential. And there it is. So your equation is going to be 4.116 times 1.323 to the x power. It gave you your exponential. All right, so it kind of looks like that. All right. Okay. Movies. Use the data from example 1, part B, in a graphing calculator to find the exponential regression model for the data. Graph the regression model on the calculator. Then graph the model from example 1 on the same screen using a dashed curve. How did the graphs compare? What can you say about the actual decline in revenue from 1 week after the peak to 2 weeks? What can you say about the actual decline in revenue from 1 week after the peak to 2 weeks after the peak compared to what the regression model indicates? Enter the data and perform an exponential regression. Okay, I've already entered the data, and let's see, on, and then my documents, and then I think I got it saved here under movies. There it is, movies. No, I don't want to save that. So there it is. I entered the data. And then I went ahead and there it is. And let's see here. Let's see, menu 4. Analyze. Menu 4, 6, 8. So there's your regression. So we have a new equation here, don't we? We've got, let's see, A is 86.2. So let's see here. Our new equation is 86.2 times, and then this is 0.575. It's a bit more precise. 0.575 to the x power. And I think the other one was 93 point. What was it? Let's see here. 95.3. 95.3. 95.3. The other one, 95.3. And remember, we approximated the B and we got 0.58 to the x power. So those are really, really close, okay? The one in the graphing calculator starts out a little bit lower, and it kind of hits the points a little bit better. Let's see here. The calculator does a better job. Of hitting the points. It starts out a little lower. It starts out a little lower. And has close to the same decay factor. And let's see, 0.575 compared to our approximation of 0.58. That's not bad. And then here's what the calculator drew. Here's what we drew, and they're very, very similar, very similar. And unfortunately, on this one here, I can't. I wish I could plot those points and stuff, but the calculator won't let me do that and let you see. Good. U.S. population in 2014 was close to 320 million. What does the regression model in Part A for the population in 2014? What does the regression model in Part A predict? Let's see here. If you put it in your calculator, it gives you about 2.2 billion. What does this tell you about extrapolating far into the future using an exponential model? Well, you should be very cautious. You should be very cautious. And you should be because maintaining a certain amount of growth is hard to do over a long period of time. It's like, have you ever sprinted? How far can you sprint? Can you sprint a mile? Can you sprint 50 yards? Can you maintain the speed that you're using? If you're running flat out for 50 yards, you can do that. But can you spread that out to a mile? It's hard to do that for a mile. And same thing with exponential growth. It's hard to maintain that for a long period of time. So number 7, fisheries. Use the data from your turn 5 and a graphing calculator to find an exponential regression model for the data. Graph the regression model on the calculator, then graph the model from your answer to your turn 5 in the same screen. How did the graphs of the models? Okay, graph the regression model on the calculator, then compare the model from your answer in your turn 5. So what did we get on your turn 5? Your turn 5. That was fisheries, right? There it is right there. So what did we get? We got 2.15.92 for B. Okay, good. So your turn 5, we've got 2.15. That's 0.92 to the x. So that was what we got. So let's do that in the calculator. And you know something? I went ahead and did it already. Fish, you didn't notice that earlier, did you? No. So here it is. I put it in. All right. And then I went ahead and graphed it. And there's the graph. So let's see here. Menu 4, 6, 8. And there it is. So what did the graphing calculator got? The graphing calculator got, let's see. The graphing calculator got f of x equals, and then we got 2.12, and then 0.917 to the x. Okay. So there it is right there. And let's see here. What if we let's graph what we drew a while ago. Okay, we got 2.15 to 2.15 open parentheses 0.92. I thought x. Let's check that. Yeah, and then we'll press graph, enter, and then menu for 1, -1, 10, and we'll put it on 1. And then here we'll put -1, and we'll put 2.5, and we'll put 0.25. All right, so how does that compare? Pretty darn close, isn't it? Pretty darn close. See, I can't really control that. Pretty darn close. This one starts out a little bit higher, pretty much the same growth factor. Not much higher. So I'd say the graphs are very close. The graphs are very close. They're both approximations. This is an approximation and this is an approximation. But the calculator does a better job of approximating than we can by hand. Solving a real-world problem using a fitted exponential function. In the real world, the purpose of finding a mathematical model is to help identify trends or patterns and to use them to make predictions. All right, so example 3. let you read through A, and then when you come back, we'll do B together. The average revenue per theater for the movie in Part B of the previous examples is shown in the graph. Note that for this graph, week 0 corresponds to week 2 of the graphs from the previous example. The regression model is y equals 5.65 times 0.896 to the x power. All right, A, from week 3 to week 4, there's a jump of over 70% or 60%. So from week 3, let's see here, week 3 to week 4, there's a jump of over 60% in the average weekly, but the total revenue from the corresponding week fell by over 30%. So what must have occurred for this to be true? And really, that can be a lot of things. Maybe the average revenue per theater. Okay, per theater. So what could have been happening here was why did the revenue per theater jump so high? I bet a bunch of theaters quit showing it. Okay, so probably less theaters showing the movie. And that may or may not be true, but think about it. You know, if every theater in Knoxville is showing this, in Maryville is showing this movie, we've got several choices. But if half of them quit showing it, then we have more people have to go to those fewer places. A new theater complex manager showing a similar summer movie in a single theater worries about how quickly dropping revenue for the first few weeks and wants to stop showing the movie. Suppose you are advising the manager, knowing that the model reflects the long-term trend well for such movies. What advice would you give him? What advice would you give the manager? Well, might want to be careful. Let's see. Be careful. Be careful about removing the movie. It kind of depends on what the other theater managers are doing. If you're friends with them, I guess you could call them and see what they're doing. And if they're removing the movie, then maybe you want to hold on to it and increase your revenues. Consider the situation in example 3B about deciding when to stop showing the movie. How does an understanding of what other theater managers might do affect your decision? Okay. Hindsight's 2020. If too many theaters are showing the movie, revenue per theater will decline. But if a bunch of theaters drop the movie and it's still a movie a lot of people want to see, then if a bunch of theaters drop it and there's still a bunch of people want to see it, then the revenue per theater for the ones that keep the movie could increase, and it might be worth continuing. So you probably don't want to drop it too soon on one hand, but on the other hand, it would be nice if you knew what the other theaters were doing. Graph the regression model for the catch in Icelandic industries to find when the model predicts the total catches to drop below 0.5 million tons. Remember that x equals 0 corresponds to 2002. Should the model be used to project actual catch into the future? Why or why not? What are some considerations that the model raises about the fishery? So let's go back to our fisheries. Let's see. My document. Fish. Okay. And there it is. Well, there. We're talking about. So maybe what we should do is press tab and then 0.5. All right, where is that going to cross? Menu 6, 4. So 17, and 17.5. So that's going to be somewhere about, let's see, 17 on to 2002. That'd be 2018. So we'll say about 2018 or 2019, somewhere around in there. Let's see. When it goes below 0.5 million tons, of course not. Should the model be used to project actual catch in the future? No, that's too far out. Too far out. Why or why not? Well, what the model does show is that there is some decline. The model shows that there's some decline, but why the decline is not known. It does not show why it's declining. It just shows that it's declining. Okay. So you need to find out why it's declining. Why is it declining? Are there more boats out there, more countries fishing that particular area than there used to be? What about the health of has there been a bunch of pollution? Is there some, maybe what's that, Red Sea or something like that in there? What is affecting? Could it be just a natural, decline that's going to, pick back up? And I say that because, like Lake Douglas, they'll have several years of really great crappie fishing, and then they'll have some lean years, and it's just a normal cycle. The graph, it doesn't tell you that. It just tells you that it's declining. It doesn't tell you why. You have to investigate and find out why. Number 10. How can you tell whether a given set of data can reasonably be modeled using an exponential function? Okay. And the way is to, if the ratios of successive values if the ratio of the successive values of the dependent variable, that's the y, are approximately equal for equally spaced values of the independent variable, that's the x, then you can use the exponential function. What are some ways an exponential growth or decay model can be used to guide decision, preparations, or judgments about the future? Well, there's all kinds of reasons. Cities, they may use like population growth models to determine their water, electric, and other infrastructure needs. And other infrastructure. I misspelled that. Infra. You saw how the fishermen, if the catch is going down, and they could model it and stuff and see if it's something that really needs attention. What are some ways to find an approximate exponential model for a set of data without using the graphing calculator? Well, let's see. You can use f of 0 for A, and then to estimate B, average the ratios of the successive terms or you can pick one that looks really, really close, but I don't ever have much good luck with that. Folks, great lesson. See you tomorrow in class, and have a good night.